Alright, we're going to begin a discussion over periodic law. Periodic law is just talking about if you arrange elements in the order of their atomic number, then we see a pattern emerge in the periodic table. The very first person to kind of try and order the elements was a man named Dmitri Mendeleev. He was a Russian chemist, and he had a similar idea to periodic law, but instead of organizing the periodic table in order of increasing atomic number, he did it by increasing atomic mass. And he thought that similar properties would occur in horizontal rows or periods. We've already talked about that. And he placed 7 elements in each of the first 2 rows, and then he placed 17 elements in each of the next 2 rows. But then he was actually able to kind of go ahead and decide that there would be some elements that hadn't been discovered yet, and he actually left open spots in the periodic table. Let's take a look at his periodic table. Okay, so here's Mendeleev's periodic table, and you'll notice that he's left some openings here. He recognized that between 40 and approximately 48, something else might go there. Okay, and then between 65 and 74, approximately 75, that there might be room for 2 more elements. That was kind of difficult for him to do because how's he supposed to know? He just decided to do that. And look here, we've got some of our transition metals over here with our alkali and alkaline earth metals. So as you can see, it's a different arrangement of the elements as we know them today when you order them based on the atomic mass. He even went so far as to predict a name and the properties of the elements that hadn't been discovered yet. Those empty spots, he decided he could tell you what kind of properties those elements were going to have even though they weren't found yet. And he actually turned out to be really close in his prediction. Okay, the problem with Mendeleev's periodic table is tellurium and iodine, just as an example, seem to be in the wrong columns because their properties didn't match all the rest of the elements in their same column. And so something was amiss there. Here's the periodic table from today, arranged by atomic number, and you can see here, hopefully, that there are several spots on the periodic table where the atomic masses are actually out of order. The atomic numbers are in increasing numerical order, but in some spots that I've boxed in, and I've tried to find all of them that I possibly can, the masses go out of order. So I'm just going to zoom in here so that you can hopefully see that. Okay, we've got 58.9 and 58.6 here. So this cobalt is actually more massive than nickel is. And the same thing here for lawrencium and rutherfordium. This one's 262 and this one's 261. We've got the same kind of situation happening with seaborgium and borium over here. So we have several situations in which the masses are actually out of order, but the atomic number is in order. And when you arrange it like this, in order of increasing atomic number rather than mass, then all of the elements in a column behave like all of the other elements in that same column. So for example, all of the noble gases are in this column. Okay, they are all gas form at room temperature. They don't like to bond with other things. They have 8 valence electrons, and that's the same case as all the rest of these elements in their columns. When you order it from increasing atomic number, they behave similarly. Okay, so the modern idea of periodic law differs from Mendeleev's. His idea of periodic law was increasing atomic mass. Ours is going to be increasing atomic number. The atomic number, as we already know, indicates the number of protons in the nucleus of an element, And since an atom is electrically neutral, meaning it has zero charge, that means that the number of protons in the nucleus needs to equal the number of electrons surrounding the nucleus, because the protons are positive and the electrons are negative. So if it has the exact same number of both of those, then their charges cancel out and we have a neutral atom. Okay, so that means if we order things in order of increasing atomic number, then all of the elements within a group are going to have the same number of valence electrons surrounding the nucleus. And that's what allows them to have similar properties and bond in the same way. The only reason that things have similar properties is because they bond like other things. So let's look. Carbon, for example, has 4 valence electrons, and so does silicon. So they will bond the same way because they both have the same number of electrons that can be involved in a bond. And that's why their properties are similar. And the same is true for germanium and tin and lead as well. Okay, let's talk about electron configuration. Go ahead and get your periodic table out, and we're going to go over the sublevels. These are the things from the quantum numbers section that we had talked about. This is the S, the P, the D, and the F sublevels or orbitals within an energy level. We're going to map those out on your periodic table. Okay, so what I want you to do is to pick 4 different colors, and we're going to box each of the orbitals on the periodic table in its own specific color. Okay, so let's do the s orbital first. The s orbital is going to be the first 2 columns here of the periodic table plus helium. It's part of the s orbital as well. So I'm going to put an s over here, and then we're going to box in these 2 columns and helium. Okay, so here is our s orbital boxed in, and helium as well. The next orbital that we're going to do is the p orbital. So that's over here, and it's going to be this whole box right here. All of the noble gases go in it, all of this from 13 over to 18. Okay? Alright, so there's our p orbitals boxed in. Now we're going to do the d orbitals, and the d orbitals are going to be this middle section here. And we are going to make sure that we include our synthetic elements down here. This periodic table is a little bit older, and so these don't have names yet. As of today, they actually do have names, and we found several more, or created several more synthetic elements, but we never really use those anyway, so it doesn't make a big deal. You will also include lanthanum and actinium in the d orbital, so those need to be boxed in the same color as your d orbital section. And let's go ahead and talk about that real quick. There are a couple of different ways that you'll see the periodic table arranged. I prefer this arrangement, which is why we use it in my chemistry class. And it has lanthanum and actinium down here because these 2 rows have special names, the lanthanide series and the actinide series, and they're named for the first 2 elements in that row. Sometimes, though, you'll see these 2 elements up here in this space so that they can be with the d orbitals where they belong. Let's take a look at the other version of the periodic table that has it that way. Okay, so as you can see here, lanthanum and actinium are actually placed up here in the D block where they belong, and the lanthanides and the actinides start with cerium and thorium. And so sometimes these are down here so that makes sense why they're named the way they're named, and other times they're not. The other 2 are included up in here. So it really makes no difference. Notice this is an updated periodic table, so it actually gives us the names of those synthetic elements, and we actually have the other synthetic elements that don't have names yet. So let's go ahead and box in our d orbitals. We need to put that this is the d orbital right here, and then we'll box it. Okay, so here we've boxed in all of our d orbital elements, and then the very last one that we need to do is to box in our f orbital elements. So let's see, we'll put in F here, and then we'll box them in. Okay, so there are our 4 orbitals all boxed in on the periodic table, and this is what yours should look like. I suggest that you box rather than shade it in because earlier in the semester we already shaded in the different family groups on the periodic table, so these should already be shaded for alkaline metals, alkaline earth, transition, poor metals, metalloids, non-metals, noble gases, rare earth metals. So boxing it in makes more sense here. Okay, so the next thing that we're going to talk about is electron configuration. That's actually why we just mapped out the orbitals onto the periodic table. This shows the arrangement of the electrons in the atoms, which is something that the quantum numbers do, but this way we'll actually be able to see it on the periodic table. In an electron configuration, each atomic orbital, SPDF, is designated by the principal quantum number first, which is the row or period number that that element is found in, followed by what sublevel we're talking about, SPD or F, and then how many electrons are in that orbital at that moment. It is continuous from the very first element on the periodic table. There is an electron ascension, which is given to you in your notes, and I'll show you that in just a second. And for some of us, it's actually on the periodic tables in the classroom, so you'll be able to refer to that other than on quiz and test days. Okay, so this is the electron ascension. It shows you what order all of the orbitals are filled in. Remember, I showed you an energy diagram so that we can see here. Remember that our different energy levels increase in energy. Electrons that are in the 4th energy level have more energy than electrons that are in the 1st energy level, and that this is the order in which they're filled. And notice here, like 4s comes before 3d, so the 3rd energy level doesn't actually get completely filled before the 4th energy level starts getting filled up. In this picture, we kind of associate our energy levels increasing in energy as we go up to the Bohr model of the atom. Okay, so we're actually able to say here's the 1st energy level, and it corresponds to this 1st energy level, and it states how many electrons are so far in that level. So here the 2nd energy level has all 8 electrons, and then the 3rd energy level has 6 of its electrons so far. So this image just kind of serves to show us the electrons being placed in their energy levels, and then how that would look on that energy diagram. So this gives us the order in which all of the electrons are supposed to be filled. The 4s and then the 3d and so on and so forth. And so this chart right here kind of does the same thing. We fill the 1s orbital, then the 2s, then the 2p, and then the 3s, then 3p, 4s, 3d, 4p, 5s, and it just keeps going like that all the way through. Okay? So let's get some practice doing some of these electron configurations, and that's what this is called. If I ask you to give me the electron configuration for hydrogen, here's how you do it. Okay, we're going to state the principal quantum number first, then the orbital that that element is found in, and then how many electrons are in that orbital for that element. Okay, so you're going to need your periodic table to do that. Okay, so here's hydrogen. Another thing I want to go ahead and have us do here is to write down the principal quantum number next to each of our rows on the periodic table. Okay, so next to each row, we want to write the principal quantum number. Okay, so we've got 1, 2, 3, 4, 5, 6, 7. Now notice that right here, 57 through 71, all of that fits right here. And then here we've got 88, 89 through 103 and 104. So all of this fits right in here. So this is actually part of the 6th row and this is part of the 7th row. So I'm going to put that in there just so we have that. Okay, so hydrogen, you're going to say the principal quantum number for hydrogen, that's 1. Then what orbital is its electrons in, S. And then how many electrons are in that orbital. Hydrogen only has 1 electron. So that's why we have 1s1. So helium, first row, so it's got a principal quantum number of 1. It's an s block, and helium has 2 electrons in that s orbital. Okay, lithium. Alright, now here's where we need to talk for a little bit. Lithium is in the 2nd row of the periodic table, so you might be wondering why I'm not saying 2s. Remember, I stated earlier that electron configurations are consecutive, starting with the very first element of the periodic table. So you have to keep filling it all up. So you would say 1s, 2, and then 2s, 1, because there's only one valence electron for lithium. So if we use this picture as an example again, notice here we've got these 2 electrons in the s orbital for the first energy level. Let's say that this element was lithium, okay, and we ignore all the extra electrons. We know that lithium has 2 energy levels because it's in the 2nd row, so its principal quantum number is 2. That means that it's got 2 energy levels. And there would only be 1 electron in this 2nd energy level. So let me redraw this. Okay, let's see. Here's the nucleus. Here's the first energy level. Here's the 2nd energy level. And let's say we're doing lithium. Okay? Alright, so we've put our electrons in. We've got the first energy level filled, and then the 2nd energy level has just 1 here. Now remember, the 2nd energy level, you have a s orbital and you have 3 p orbitals. Let's revisit that, okay? If n equals 2, then that means L is going to be n minus 1. So L can be 0 and L can be 1. So that's an s orbital, that's a p orbital. Okay, then you've got m sub L. It can be 0 here if L is equal to 0. And it can also be all values from negative L to positive L. So if L is 1, then it's going to be negative 1, 0, and 1. That is our 3 p orbitals right there. Okay, and here's our 1s orbital. But since we're in the 2nd energy level, that's actually the 2s orbital. And then we've got the spin values. So we've got the plus 1/2 and we've got minus 1/2 of values for each of those electrons. Now, this orbital can hold 2 electrons, this one can hold 2, this one can hold 2, and this one can hold 2. Alright, so the s orbital right here, it's got its 2 electrons in there right now. Okay, then that's for the first energy level, that this is n equals 1, this is n equals 2. So the 1s orbital's got both of its electrons. The 2nd energy level's only got 1 electron, which means it belongs in the s orbital. We don't have any electrons in the p orbital, and since this is the very first electron in the s orbital, it's going to be a clockwise spin, so it would be a plus 1/2 here if we're revisiting our quantum numbers. Okay, so we just have 1 electron in the s orbital, for the second energy level. So that's why we say 1s2, that is the 2 electrons in the s orbital for the first energy level, and then 2s1, we have 1 electron in the s orbital for the second energy level. Okay, and then we could do beryllium, the very next one after lithium. So that's the second electron in the s orbital for the second energy level. Remember, each orbital can only hold 2 electrons, so that s orbital is full now. Okay, then we could jump over and do boron. So you're going to have all of the electrons that came before it, and then we need to put our first electron in our very first p orbital for the second energy level. Okay, let's see if we can do carbon. Alright, okay, so here's carbon over here. The way I teach this is to put your left index finger on the very first element, hydrogen, okay, and then you're going to slide your right index finger over until you get to the end of an orbital. And if you haven't reached the element you're talking about yet, then you write down the configuration, okay? Alright, I've made some space so that I can write carbon's configuration down here with you. Alright, so we're going to start out with hydrogen and we run to the end of that orbital, which ends right here. We have not reached carbon yet, so we're going to write down what we have so far. That's going to be 1, we're in the s orbital, and we've hit the second electron in the s orbital. Okay. Then we keep on moving, so we're here at lithium now. We run to the end of this orbital, which stops right here. We can't go past this yet without writing it down. So we're in the second energy level, we're in the s orbital, and we've hit the second electron in the 2s orbital. So we write 2s2. Then we jump over here to our p orbital. So we start right here, and boop, we end with carbon. So we're in the second energy level, so we write 2. We are in the p block, so we write p. And then we hit the second electron in that p orbital. So we would write 2 for 2 electrons. So we have 1s2, 2s2, 2p2. Okay, a couple of things about how to write this electron configuration. Do not put commas in between each of these things. That is incorrect to put commas in there. Okay. Also, you need to make sure that the numbers that you write down are superscripts. Okay, so that means that they need to be above the letters. So notice how I have mine above. They are not big numbers sitting next to the letters, so you should not write it like this. Okay, that's incorrect as well. Alright, this is the correct way to write that configuration. Okay, so let's transfer that back down to our examples, our practice. Okay, so we had 1s2, 2s2, 2p2. Alright, I want you to see if you can figure out nitrogen and oxygen, and then we'll come back in just a second once you've had time to do those. Okay, so for nitrogen, I got 1s2, 2s2, 2p3 because it's got 3 electrons in the p orbital. And oxygen is 1s2, 2s2, 2p4 because there are 4 electrons in the 2p orbital. So hopefully you understand that now, how to do electron configuration. There's homework in your notes, which you should be assigned pretty soon, if not already, and that's how you go through and do that. I do want to give us one more, or maybe actually 2 more examples of elements that occur further down in the periodic table, specifically in the d orbital and in the f orbital. I want to get a little practice here with some elements that are a little bit beyond the p orbital. So iron's in the d orbital and neodymium is in the f orbital. And I think we need to get some practice doing electron configurations with those because they have a little bit of a special situation that we need to talk about. Okay, so here's iron in the D block, and here's neodymium in the F block. Let's get the electron configuration for iron. We start out with hydrogen as usual. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we're ready to move into this D block. This is not the 4D, this is 3D. Anytime you move into the D block, you need to subtract 1 from the row number. I'll tell you why in just a minute. So here we have 3D, 1, 2, 3, 4, 5, 6. Okay, so let's go write that down. Alright, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. And that's our electron configuration for iron. Okay, let's go take a look at neodymium. Okay, here's neodymium right down here. We're going to start with hydrogen as usual and go on through. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we're ready to move into the D block. So we've got our 3d10 and then 4p6. When we move back into the P block, we go back to the regular row number. So 4p6, 5s2, 4d10, 5p6, 6s2. And now we need to decide, do we go into the D block or do we go into the F block? Let's check our electron ascension to find out. Okay, so here we are right here at 6s, and then the next block we move into is the F block. Okay, so 6s2 and then into the F block, and when you move into the F block, you subtract the row number by 2. So this is 4f1, 2, 3. Alright, let's go write that down. Alright, so we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f3. Okay? Now I told you that I would tell you why you subtract by 1 when moving into the D block and why you subtract by 2 when you move into the F block. So let's take a look at that. It all has to do with quantum numbers again. Let's see, if n equals 2, then L can be 0 and 1. That stands for an s orbital and a p orbital. If n equals 3, then L can be 0, 1, 2. So that stands for S, P, D. So notice that the very first time that a d orbital appears is in the third energy level, which is why you have to subtract by 1 so that we can get back to 3 for the very first d orbital. Okay? If n equals 4, then L can be 0, 1, 2, or 3. So that's S, P, D, and F. So you'll notice that the very first time that an F orbital appears is when n equals 4, the fourth energy level. So that's why you have to subtract by 2 when you get down to 6, so that you can end back up at 4, because 4 is the first time that an F orbital appears.